Hello everybody, my name is Engelken, and today I want to talk about how to do very large spiking neural network simulation using Julia. I just finished my PhD at the Max Planck Institute for Dynamics and Self-Organization, so there was some misconception about the MPI on my name tag. I like message passing interface, but it's the Max Planck Institute. I was supervised by Fred Wolf, and I did my PhD on chaotic neural circuit dynamics. So information in the brain is processed by the coordinated activity of huge neural circuits. It's a challenge to understand how this generates function and information processing. From a dynamical systems perspective, high-dimensional, nonlinear interacting systems are very often chaotic. And being chaotic is not obviously a good strategy if you want to design an information processing machine. So if a system is chaotic, the future is unpredictable. So we use tools from nonlinear dynamics and information theory to understand under which conditions neural networks are chaotic and what this can tell us about information processing in the brain. So you might be familiar to modeling neural circuits by artificial neural networks. However, the data format your brain uses to process information is very different. So in an artificial neural network, the time is discrete and neurons communicate with continuous variables. However, in a neural network in the brain, the single neuron dynamics emits pulses of action potentials, mathematically speaking point processes, and it's not clear how their collective dynamics processes information. And so I want to use tools from nonlinear dynamics to put numbers to this information processing to reverse engineer how this brain evolved over millions of years to optimize information processing. So we need people like you to better understand such complex information processing devices. So single neurons are described by their membrane potential. So you have the neuron dynamics is a function of the membrane potential itself, V, and by some external input. And together they form a collective chaotic dynamics. So in dynamical systems, we distinguish as two classes of systems. So if a system is sensitive to small changes of initial condition, we call the dynamic stable, and therefore you have a negative largest Lyapunov exponent. If infinitesimal changes of initial condition grow exponentially, such a system is chaotic. And if a system is chaotic, there's always a dynamic entropy production called Kolmogorov-Sinai entropy associated with this dynamic entropy, with this chaos, because nearby initial states are being pulled apart by the chaotic system dynamics and become distinguishable over time. So this entropy production measures the rate by which noise is written from the microscopic state into the network state of your dynamical system. And so we want to put numbers on it and measure it in terms of bits per second. And so measuring entropies in high-dimensional systems, as you might know, is intractable because of the curse of dimensionality if you want to measure it directly. However, we can measure it indirectly from the Lyapunov spectrum. Lyapunov exponents measure the exponential rate of divergence and of convergence of nearby trajectories. And the sum of the positive Lyapunov exponents give under mild conditions this Kolmogorov-Sinai entropy production. And based from the Lyapunov exponents, we can also calculate the attractor dimensionality, which tells us something about the collective properties of this complex dynamical system. So this is the equation we want to solve. It's a coupled differential equation. The single neurons are described by the membrane potential V, and they are a function of the membrane potential itself, a function of some external input, and they get feedback from their connected neurons. So whenever neuron J sends a pulse with coupling strength Jij to neuron I, this receives a small increase of voltage or decrease depending on the sign of Jij. Now, there are great packages in Julia, like differential equations, and the obvious approach would be to plug it in there and hope for the best. However, we want to understand huge, like millions of neurons in a spiking network simulation, and so we decided to use a different strategy. Also, we care about infinitesimal perturbations, so better be sure that your solution is actually correct. So what we do is we solve the dynamics exactly between spike times. This is called an event-based simulation. So we derive an exact firing map from one network state in the network to the next spike time. And then what you have to do is the network simulation consists of 4 simple steps. First, you have to iterate through all neurons to find the next spiking neuron. Then, secondly, you have to evolve all neurons, so the internal dynamics, to the time of this next network spike. Then you have to update the receiving neurons, so those which are connected to the spiking neuron. And finally, you have to reset the spiking neuron. And you do this over and over again, and by that, gradually, you move forward in time, and you can precisely, with machine precision, simulate your dynamical system. So the only ingredient you need is that your single neuron dynamics can be solved analytically from one spike to the next. And so this gets even more convenient if we map the voltage dynamics, which is nonlinear in time, to a linear dynamics. So instead, we move from voltage to phases phi, and then we at each, the perturbation, the evolution forward is trivial. We just have to add the phase difference, and the only non-trivial step is if a neuron receives an external pulse, we have to move back to the voltage representation and go back to the phase representation. And this is called a phase transition curve. It tells a neuron, as a function of its phase, how it should change its phase if it's receiving an external input. All right? So I'll just quickly show you this to you in a toy example of the most simple chaotic neural network we can think of. It's a network consisting of 3 neurons. So I import the plotting libraries and static arrays because it's so small. Makes sense to use static arrays. Now it starts the function. So our phase space is now 3-dimensional, and what I want to calculate is a 2-dimensional section through this 3-dimensional phase space. This is called a Poincaré section. So first I set the number of spikes to 10 million. Then I define my topology. So this is an adjacency matrix telling which neuron is connected to what. Here's C is the effective coupling strength. Phi is some initial state, which does not matter so much because we only care about the long-term properties. Then we want to initialize the phase history because that's what we want to record. And now the main simulation starts. So for the number of spikes we want to simulate, we first have to find the next spiking neuron, just find max of our vector phi, the phases of the neurons. Then our threshold minus the phi max gives us the time to the next spike, our dt. We have to evolve the all phases till the next spike here. Then the index j, that's the index of the spiking neuron, gives us the jth column of the topology, gives us the index of the connected neurons. The receiving neurons, or a fancy word for that is the postsynaptic neurons. And now the only non-trivial line in this program is the following. We have to update the postsynaptic neurons, and in this case I choose a quadratic integrated phi neuron, and then this phase response curve looks like the following. We have to evaluate an arcus tangens and tangents. And inside this function is C, the coupling strength. Now the final step is we have to reset the spiking neuron, and whenever neuron 1 spikes, we append the phase of neuron 2, 3 to our phase history, and that's it. And we plot it at the end. So if we now run our network of 3 neurons for 1 million spikes, well, this takes some time. Okay, what we see here is a Poincaré section, which is a slice through this chaotic phase space. So on this axis, you see the values of phase 2 here, and the y-axis, the phases of phase 3, and each single dot is one state of the network. And so you see it does not fill homogeneously the whole plane, but instead there are typical patterns, and this is what tells us information about the geometric properties of this chaotic attractor. So the whole thing, 10 million spikes, just took less than 5 seconds. And you can actually write this in a minimal version, just in like 8 lines of code. You can run a total, complete spiking neural network simulation using Julia. Then there is a more fancy way of writing that without arrays. It takes a bit longer, but if you run this version, then the whole thing runs in less than 1 second. Okay. Yes? No, whenever neuron 1 spikes, I record the phases of neuron 2 and 3. So if you think of this room as activity of neuron 1, activity of neuron 2, activity of neuron 3, whenever the trajectory hits the roof, I make a dot on the roof, and then at the end I get this picture. Just project this on the roof. Okay? Okay. All right. So, but that's just a toy model. What I really want to understand is very large spiking neural network dynamics and quantify them. So, so just to recapitulate, we had this exact firing map. The conventional algorithm, which I just described, is you map your membrane potentials to a phase. Each dot here signifies 1 neuron, and then you iterate through all neurons, find the maximum phase, push all neurons forward by this increment, and subsequently update postsynaptic neurons. And obviously, this is order log n, because you have time complexity of order n, because you have to iterate through all neurons to find the next spiking neuron, and you have to push all neurons forward in time. And so to measure this, here is the CPU time per network spike as a function of network size. This is 1 square millimeter of layer 4 cortex. Just to give you an idea of like sizes in the brain, this is a barrel column that's a functional unit of a rodent. And here, this is the number of people who attended Donald Trump's inauguration. No, sorry, it's a cortex of a large mammal. And so this conventional algorithm scales linear. So that's, of course, not good if you want to run very large network simulation. So during my PhD, I developed a novel way to make this much faster. And there are 2 basic tricks here. Yes, Tim?
Why isn't it order n squared? Because presumably more neurons, you have a shorter, less you can evolve forward in time before you get to the next spike also.
Oh, that's true. So what I was measuring here is the time complexity for 1 network spike. So there's a CPU time per network spike.
Oh, per network spike.
So if you want to simulate for a fixed number, for a fixed time, this would indeed be n squared, exactly. Thank you for making that clear. So the novel algorithm has 2 tricks. The first one is, instead of pushing all neurons forward in time, we go into a co-moving reference frame and just push threshold and reset backward. And then the second trick is, I use a data structure. So the problem is we have to find the next spiking neuron by iterating through a vector of all states. And this is, of course, slow for large networks because we have n neurons. Now, the solution is to put the neuron states in a mutable binary heap. This is a data structure which used to be in JuliaCon, is now in the package datastructure.gl. And this allows efficiently finding the next spiking neuron and efficient state update. So for those who don't know, binary heap is a data structure where the parent element is always larger equal to the children element. And so finding the next spiking neuron is trivial. It's just the top of the heap. But now if we, for example, want to update this neuron 0.7, it receives a negative pulse. 0.3, you can see that the heap order is not fulfilled anymore. So what we have to do is we have to percolate down through the heap and so exchange these 2 and now exchange these 2, and now the heap order is restored. Now as the number of neurons per layer grows exponentially, this just uses on average a logarithmic number of steps. And therefore, this can be made very fast. And so actually, within Julia, this is implemented in arrays. So you map your whole tree structure into an array, and finding the children elements is just a bit shift operation and a small addition. So you can make this really, really fast. So using this for a fixed number of neurons, for a fixed number of synapses per neuron, we can reduce the time complexity to order log n. And so this allows now to simulate very large spiking networks. So just to give you an idea, using the old implementation, running 1 million neurons for 100 seconds simulation time would take more than 3 years if you do it on a single CPU. And using the novel algorithm, this takes less than 1 hour. So there's a drastic speed up. So I should again make clear, this is only for a fixed number of synapses per neuron, and this only works if you can actually solve our single neuron dynamics analytically from spike to spike. And okay, so now next problem comes. If you always run 10 to the 9 neuron simulations on your cluster, then your colleagues start complaining and getting cranky because their cluster jobs starting being erased because you're using too much memory. Actually, doing 10 to the 9 neurons is impossible because in a naive way, well, it's clear that the topology would scale quadratic. So here's a naive implementation to generate a network topology. N is the number of neurons, K is the number of synapses. So our probability of wiring is K over N minus 1. And now we seed our random number generator and generate random numbers. And whenever they're smaller than P, there's a true. So that generates a Boolean matrix. We run this. Well, this generates an n by n matrix. And of course, that's a very bad idea if you want to run very large networks. So instead, the next clever idea is, so yeah, if let's say neuron 17 spikes, you just have to look into the 17th column of this matrix, of this bit array. Now this, of course, is a not so clever idea if you want to run large networks. So instead, what you can use is a sparse network topology. So we can just use the sprunt with a Boolean argument, and then this will generate a sparse matrix with Boolean entries. And but still, we have to save n times k entries, and if you want to run millions or billions of neurons, that's still too much for at least conventional clusters. And so instead, what I did is I used the index of I generated the network topology on the fly. How do I do that? So neuron, let's say J equals 18 is spiking. I reseed the random number generator by the index of the spiking neuron. Now, in a loop, I generate connect the neurons, the postsynaptic neurons, and that's, of course, a lot more memory friendly. Well, now the problem is, if you benchmark this, reseeding Mass and Twister is actually not so fast. So if you want to reseed Mass and Twister, at each iteration, it costs an order of 12 microseconds, which might sound not so much, but you want to do it all the time, like in a very large simulation. So instead, the solution is to use a faster random number generator, and there's this great package, randomnumbers.gl, and there are very efficient random number generators from the XOR shift family. For example, the Xoro Shiro 128 star, that's the fastest one. And if you do exactly the same again, benchmark it, it's just 18 nanoseconds, so it's almost 1,000 times faster. So this is really super fast. And so now we put this into our network simulation to generate the network topology. So our colleagues are friendly and the group atmosphere is happy. Okay, so now comes the minimal example of a large spiking network simulation. So we import the data structures, the random numbers.gl. Now we define our get index and set index for mutable binary heaps. They don't exist yet. And so we have to import from base get index, set index. Then now we define them. That's the nice thing about Julia, that you can actually, if you don't like something about base, you can directly change it, or if you don't understand it, you can see how it's implemented and see whether you can make it faster. And so now we have our own methods, get index and set index. So set index has now 126 methods instead of 125. And now starts the spiking network simulation. So we have a function that's just a minimal code to give you an idea how to actually do it. At the end, First, we define some neuron parameters. In this case, I use the so-called leaky integrated fire neuron model. So I have to define an external input, which depends now on the parameters that I put in, the membrane time constant, the number of synapses, the coupling strength, J0, the desired firing rate. Now, W is my phase velocity, C is the effective coupling strength. This is just a function of the external input and the number of synapses per neuron. I have to set the threshold and the shift. So the initial global phase shift is 0, and then subsequently we will always shift this further and further. We initialize our random number generator. Now we generate the mutable binary heap. Of course, if you do that in larger simulation, you can do this in place and save a bit of memory. We initialize and pre-allocate the spike raster and the vector of the receiving neurons, the postsynaptic neurons, and now starts the main loop. So it's very simple, very similar to what I told you before in the 3-neuron simulation. So first, we have to find the next spiking neuron. So there's this function top with handle for binary heaps, which give you the maximum value in its index j of the spiking neuron. Then we calculate the time, the next spike time in the network. We shift the global phase by this global spike time. So that means we evolve the network state forward in time. Now we reseed our random number generator by the index of the spiking neuron and a seed for our network topology, because maybe we want to run different simulations with different network topologies. Now we sample the receiving neurons, and for that we again use this fast random number generator. And here's just a small loop to avoid self-connections, so that the neurons actually don't spike to themselves. And so now the only non-trivial part is here the phase transition curve, which receives the state of the system, phi, the postsynaptic index, the shift, the global phase shift, phi shift, W, the phase velocity, and C, the coupling strength. I'll define it in a second, how this phase transition curve looks like. And then we have to reset the spiking neuron and store the spike raster. So that's it. Let's hope it works. So just quickly, we have to define the phase transition curve. In this case, it looks very similar. In this case, I choose the phase transition curve of a leaky integrated fire neuron. So let's also define this. Now let's define some desired parameters. Let's say we want to run 100,000 neurons for 100,000 spikes, so with a firing rate of 1 hertz. So that means we have 1 second of simulation time. We first compile our code, and now we actually run the simulation. And like in less than 1 second, we were able to generate a spiking network simulation of 100,000 neurons. So that's it. All right. So what is this actually good for? Well, yeah, I should quickly say the idea with the generating the topology on the fly, that I didn't invent that. I saw that earlier from Rob Rosenbaum and Eugene Itzikevich. Maybe somebody else has done it before. Okay, so now the next thing is we want to calculate the Lyapunov spectrum. Now, if you want to calculate the Lyapunov spectrum, you have to evaluate a Jacobian along the trajectory. So basically, along the trajectory, we want to probe the tangent space and see how small perturbations evolve over a long time. So this requires to multiply the Jacobians one after the other and to evaluate the properties of the long-term Jacobian. Now the problem is, of course, it's a huge matrix multiplication at every network spike. So this means order of n squared times m operations, where n is the number of neurons and m is the number of Lyapunov exponents we want to calculate. So this is definitely not a good idea. So the solution is we can make use of the sparsity of the Jacobian matrix and reduce this to order of 2k times n operations, where k is the number of synapses per neuron, and we said we can keep that fixed. So this means this whole matrix multiplication is super fast. And then I built my own custom in-place matrix, sparse matrix multiplication, which is cache-friendly, so it respects the column major ordering of the arrays and makes use of the specific structure of the Jacobian. By that, we can tweak it a little bit faster, and we avoid any memory allocation. And so this now allows us to calculate Lyapunov exponents also for very large networks. I should say that if you want to calculate the whole Lyapunov spectrum, that's still intractable because you have to do a QR decomposition from time by time, and that scales with n to the 3. But if you don't just want to calculate a fixed number of Lyapunov exponents and crank up your simulation, then you don't have to think about this QR decomposition so much. So what did I use this for? Well, in my PhD, we studied the design of neurons that generate less chaotic neural circuit dynamics and thus reduce the entropy production and lower the attractor dimensionality. And the functional implication of this is they are then being easier controllable from outside. And secondly, I investigated the role of input spike trains, and I found there's a suppression of chaos if you drive a network strong enough. Now, and if you drive it even stronger, then there's a transition to complete network state control, meaning that the network state is independent of the initial conditions. Now, interestingly, these two transitions are different, and in between there's multi-stability for spiking input. And just quickly, so here you see the asymptotic form of the largest Lyapunov exponent. So that's the largest Lyapunov exponent as a function of a biophysical parameter. It's called the spike onset rapidness, basically the speed by which action potentials are generated once the internal dynamics is beyond an unstable fixed point. And before, we didn't really know what happens in large networks. And now using this novel implementation, I ran up to 150 million neurons networks, and I found that the largest Lyapunov exponent saturates for large n. And so as a physicist, we always like to understand how things scale, and this gave us the scaling properties, how this peak position scales with different network parameters. This helps us to better understand the fundamental dynamics of such circuits. Now, the second application is very soon experimentalists will give us a whole wiring diagram of actually cubic millimeters of the brain. And just in preparation for that, I already wired up a cortical circuit model with 80,000 neurons and a layered structure and realistic wiring probabilities between the different subgroups. And so using this, I could then test whether what I found earlier with random networks would also work in a more structured network. And I found that indeed the largest Lyapunov exponent as a function of this biophysical parameter, the spike onset rapidness, also is greatly reduced if you increase the rapidness, and the entropy production given by the by the sum of the positive Lyapunov exponents, that's drastically reduced for a realistic range of rapidness. So we can also make sure that the Lyapunov spectra actually converge also for very large simulation over different initial conditions, and using big floats is also a way to check whether our numerics is actually okay. And just very briefly at the end, I further investigated spike-driven networks. I think I can't go into the details for that, but if you drive networks by spike, they behave very different when you drive them by external white noise. That's at least what I found in these simulations. And this might be relevant because you can think of your brain as a network of networks driving each other with action potentials. So we want to understand under which conditions can one network control activity in another network, and this gives us a tool to quantify this. So just to finalize my Julia experience, so Julia was very helpful to find bottlenecks of earlier implementation and write a new efficient implementation in very few lines of code and optimize it within Julia. And so helpful features for me as a Julia user, not a Julia developer, was that there are super fast loops, there's easy profiling and visualization, it's easy to track memory allocation, it's easy to track down type instabilities, it's easy to use this fast random number generator, check the precision using big floats was helpful for me, and so the data type I needed, the binary heap, was available directly off the shelf. So of course you could run all this also in C++, but you probably could not do it in 100 lines of code. And so one thing with which I want to end is I really like the very transparent Julia core code, and more generally I think scientific computing needs reproducibility and transparency. It should be easy, that you can understand other people's code. And actually, I think it's one of the greatest strengths of Julia, that if people use Julia, you can actually understand what other people do and can reproduce it. And I think that's very important for the scientific progress. So just to finish, I want to thank my supervisor, Fred Wolf, Michael Monteforte, who started with chaos, with the study of rapidness and chaotic networks, the other people from our chaos crew in our group, then the Julia community for random numbers.gl, data structures.gl, the people on Gitter, and fruitful discussions with Tim Hawley, Chris Rakaukas, and Simon Danish. And thank you all for your attention. It was a great conference. I really liked it.